So this is lecture 6 of problem solving. What we're going to do today is we're going to do some consequences of the arithmetic mean, geometric mean. We're going to see how you can use it to solve a problem you might actually care about. And then as time permits, we will talk a little bit more about recurrences and hopefully finish up that topic. Probably won't get to do all of that today, so we'll probably finish recurrences on Monday. The method of divine inspiration, which I've mentioned before, is a wonderful method, but it is a little bit fickle and it's sometimes hard to count on it working. So I want to talk to you about some concrete things you can always do, both for recurrence relations as well as for solving inequalities. So we had before the following. Consider a plus b, b plus c, c plus a, greater than or equal to 8 a, b, c. And I think we might have said, assume a, b, and c are greater than 0. Sometimes it's nice to assume that it's greater than or equal to 0, so you're looking at a compact set. For a lot of the results from real analysis, we want to have a compact set. There's a beautiful theorem that says if you have a continuous function on a closed bounded set, which is a compact set, it attains its max and minimum. When I don't include the boundaries, things are a little bit different. Well, if I include either a, b, or c equaling 0, not going to be that much of a problem. The inequality will clearly hold in that case. Okay, so the question becomes, how would you prove something like this? One of my go-to facts is Lagrange. Love Lagrange multipliers. We would need to choose a constraint function, and we would need to choose a function to optimize. We have two real choices for constraints. Any thoughts? Do you want to do a plus b plus c, or do you want to do the product? And I'll call that S for sum, or a, b, c equals p for product. Any thoughts? Yes? I said it might be. No, okay, if we do the sum, it is bounded. So that could be an advantage to do the sum. Turns out it's not going to work well to do the sum. But in all fairness, it's not going to work well to do the product either. So no matter what you choose, it's going to be bad. So let's try doing the sum. We could actually rewrite this if we wanted to. We could rewrite this as s minus c, s minus a, s minus b. So I could write this if I wanted as s minus a, s minus b, s minus c, maybe minus 8 a, b, c. And we want to try to figure out what's the smallest value this attains. Right? And so if we take a equals b equals c, we would notice that we would get equality. I believe. Yes, we would get equality. So it will be 0. So note is 0 if a equals b equals c. So we could call this f of a, b, c set gradient of f equal to lambda gradient of g. G of a, b, c is just a plus b plus c minus s. You don't have to put in the minus s if you want. If I shift g by a constant, I'm not going to change its gradient. So the question is, do I want to describe my surface as it's all the points a, b, c, such as a plus b plus c minus s equals 0, or do I want to describe it as the set of all points a, b, c, such as a plus b plus c equals s? Makes absolutely no difference. And so I would get that the gradient of g is just 1, 1, 1. And then I would go through and I would take the derivatives and I would get a nasty set of equations. I've played with it a little bit. I wasn't able to find a nice way to proceed. I just wanted to set up the problem so it's clear as to how you would start. If this doesn't work, you can try doing it the other way. We could also expand things out. Whenever you have a term a, b, c, that's going to be the same as something over here. Are there nice simplifications you can do? There may be a nice way of looking at this. I did not find it. But there's a better way. And this is one of the themes of the class, is to try to figure out what's really going on. This is a problem I'm giving to you. But that doesn't mean it has to be a problem in isolation. So we talked a little bit about how we should view this. Okay? So since the Lagrange multiplier method is not going to work, I'm going to completely destroy it right now. Goodbye. Gone. So how did we decide that we should view the number 8? View 8 as 2 to the third. And more generally, we might conjecture that a1 plus a2, a1 plus a3, maybe dot to dot, all the way down to an minus 1 plus an should be greater than or equal to I'm sorry? Oh, did I miss that? So let me write it in a better way. The product may be 1 less than or equal to I, strictly less than j, less than or equal to n, of ai plus aj. Because when I'm writing it the other way, it's not clear how I'm ending. Is that what we want to study? Or do we want to study the cycling thing? a1 plus a2, and then the next one would be a2 plus a3, dot to dot, an plus a1. So the bottom one is just going down in order. This one is looking at all possible pairs. Right? In general, there are going to be more possible pairs than here, correct? So how many pairs would there be in this case? N choose 2. So this is n choose 2 pairs. Right? How many pairs are there over here? N pairs. And these are equal if n equals 3. So this is one of the things I really love about choosing this as the problem. It's not immediately clear which way do we want to generalize. Do we want to generalize to all pairs, or do we want to generalize to just something like this? What would be the correct thing over here? Well, the fact that we have 3 terms here, if we were to generalize, let's give things units. If I think of these as meters, this is meters cubed, and this is meters cubed over here. The units work nicely. If I were to try to do something here, I probably wouldn't have just a product of a1, a2, an. It would seem like it would be the wrong degree. That's not to say that the inequality can't be true, but it would be strong evidence against something like this going to a simple product, that this is probably the right way to generalize. But maybe there is an equality with this. All right, so if we think that this is the correct generalization, we should consider maybe the n equals 1 term, the n equals 2 case. And that could give us intuition on how to attack the general case. All right. We are fortunate that the n equals 1 is not too bad. So we have a is greater than or equal to 0. Prove a. Oh, no, let's see. This could be interesting as to how would we do it if we just have 1 term. Can we even talk about it when n equals 1? No. Can't talk about it when n equals 1. So for this problem, probably the simplest thing we can start with is n equals 2. So if n equals 2, we would have a and b greater than or equal to 0. We want to prove a plus b would be greater than or equal to So do we think that this would be true?
I think also.
So maybe there is an n equals 1, and maybe we're just looking at things the wrong way right now.
The thing with n equals 2 is we cycle through it, right? So we start with a1 plus a2, and we end with an plus a1. So if we want to do that.
So if we cycle with an plus a1, we would actually have an a plus a term, right? Oh, it would be a plus a would be the first one.
If you want to do it that for n plus 1, it would be a plus a is less than or equal to 2a.
So maybe we want to write for n equals 1, a greater than or equal to 0, and then a plus a greater than or equal to 2 to the 1 times a.
Yeah.
Maybe that's the right way to write n equals 1. And that will work. This is not a difficult inequality to prove due to time constraints. I don't have time to get into the details of this, but I will leave this as an exercise. It's a shame Kayla is not here for today. Now for n equals 2, we have a and b are greater than or equal to 0. So it would be a plus b, and then we cycle around to b plus a. So again, you've got to be very careful how you try to do the other cases. And we want to show that this is greater than or equal to 2 squared times ab. Yes. Okay.
Basically, if you just have them equal each other, they should be equivalent.
Correct. And if we take a equals b, we'll get 2a times 2a is 4a squared. All right. So we want to prove this inequality. Now there might be something you notice here. What's the left-hand side?
If you divide by 2 squared, you have the arithmetic.
Yeah. The left-hand side is a perfect square. So if we take square roots, we get a plus b, and then will be greater than or equal to, and I'll put a question mark because we don't know this is true yet, versus 2 square roots of ab. Well, now dividing by 2, as has been remarked, we get a plus b over 2. Is that greater than or equal to the square root of ab? Yes. This is the AMGM. So again, I'm trying to go through the thought process and not just jump to the way to do n equals 3. I really think that by doing some simpler cases and building intuition, one of the biggest advices you always get in low-level math classes is draw a picture. Most of us, just nod our heads, okay, 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 and then we don't even bother drawing a picture, we just go straight to the algebra. The best advice I can give you in stuff like this is try simpler cases and build intuition. So what we're really saying here is we just have the arithmetic mean, geometric mean inequality. And that a plus b is going to be greater than or equal to square root, 2 square roots of ab. Now because we have the 8abc for n equals 3, we could write it as a plus b over 2, b plus c over 2, c plus a over 2. Is that greater than or equal to abc? And now the suggestion is use AMGM 3 times. This will be greater than or equal to the square root of AB. This will be greater than or equal to the square root of BC. This will be greater than or equal to the square root of AC. And now when you multiply everything together, we'll have square root of A twice, we'll have square root of B twice, we'll have square root of C twice. And when you multiply it, you get A plus B, B plus C, C plus 8, all over 8 is greater than or equal to ABC. So it really just follows from the AMGM. So what's tricky about this is you're doing the AMGM 3 times. And so you want to take a look at this complicated thing and look at applying the AMGM to parts of it. So the question is, what is the best way to see something like that in the future? One part is always, whenever you have an expression, is there a sub-expression lurking inside that's easier to understand, that you can work with first? Break it down into lots of simpler problems. And then you piece them together. Okay, any questions about this? All right, so this was, I think, a really good problem. I did some searches to try to find some other problems. I like this next one. And so I'm trying to find problems that have nice twists in applying the AMGM. If it's really clear what F is and really clear what, really clear, how to apply it, it's not so interesting. How many of you remember your sequences and series convergence rules from Calc 3 or real analysis? How many of you remember that there exists such a thing as, there's the ratio test, there's the root test? Okay, am I still speaking English? Okay, good. Do you remember the comparison test? Comparison test is wonderful. If you want to show a series converges, let's say the series is non-negative. You just show that it's bounded by a series that converges and it must converge. Or if you want to show it diverges, you show that it's always greater than a series that diverges. The difficulty is finding what to compare it to. The ratio test and the root test, they're like the quadratic formula. There's really not that much thought that needs to go into, well, let's see, I'm going to take the nth root. I'm going to take the ratio of the n plus first term over the nth term. It's really clear what you should do. Then maybe you have to be a little bit clever as you grind through the algebra. But the way you start a ratio or root test, it's straightforward. There's no mystery. The comparison test, you have to find a good thing to compare it to. That's the difficulty. The comparison test is the hardest one to do. Now, interestingly, the way things like the ratio and the root test are proved is actually using the comparison test. But it does the comparison test for you in the background. It often compares it to a good geometric series. All right, so let's consider, could have left the word consider there. I think I want 2a cubed plus b cubed greater than or equal to 3a squared b, and I want a and b greater than or equal to 0. Okay. So there is an asymmetry between a and b. Thoughts on how we might want to attack this? Yeah.
Maybe write it as the 2a cubed is a cubed plus a cubed.
Yeah.
When you divide by 30.
Yeah. I mean, the 3 is telling us we want 3 terms. We have 3 terms on the right. We should just write this as a cubed plus b cubed versus 3aab. And now we can apply the arithmetic mean geometric mean. Right? So apply AMGM to a cubed, and b. If I divide by 3, this is the arithmetic mean. So a cubed plus b cubed over 3 will be greater than or equal to the cube root of a cubed, this is probably a b cubed to the 1/3. Well, that's just going to become a squared b. So you can often symmetrize or expand. When you see the 3, you should be thinking, if you're going to use the AMGM, I want 3 terms. How can I get 3 terms for something like this? And one thing is to expand out. Now, the nice thing is you have a 2 and a 1, so there are some clues that there's a 3 lurking in the background. It is hidden. And so a lot of the math competitions and stuff like this, it's designed to hide what you're trying to use. Now, I actually like to use inequalities like this in work that I'm trying to do, and trying to prove things. And so the difficulty is always figuring out what's the right way to apply something. Okay, any questions on this one? All right, so let's do another one. And I'm trying not to know what these answers are, but I do have the answers written down in case we get stuck. So one of the problems, of course, in teaching a section on the AMGM is it's pretty clear what you should be using in attacking these problems. The class gets a little bit more interesting the deeper we go, and we have more techniques, and it's no longer clear what you're going to do. So let's consider, this time I want a to the 4th plus b to the 4th plus c to the 4th greater than or equal to abc, a plus b plus c, and I want everything to be greater than or equal to 0. Okay. This looks a little bit worse. Now, one thing that is nice is at least the units seem to be right. If I put a in meters, the left-hand side is meters to the 4th, the right-hand side is meters to the 4th. So how would we attack something like this? What we did the last time was we broke things up. Or if you go back 2 times ago, we broke things up and we looked at A plus B by itself and then B plus C by itself. Maybe that could be a good idea here. Any thoughts how I should view the right-hand side? So how should I view the right-hand side? So what can I do to the right-hand side? Not much I can do. I can expand. So I can do a to the 4th plus b to the 4th plus c to the 4th greater than or equal to, and I'll put a question mark, a, b, c plus a, b, b, oh, almost ABBA, plus a, b, c, c. When you see this, what should you be thinking? So what should you be thinking when you see a term that's A, A, B, C? Well, there's only one real topic for today so far. So we're thinking arithmetic mean, geometric mean.
Yeah.
Right? So let's study.
Just take all the terms on the right
Mm-hmm.
and assume, that's the geometric mean for 2a to the 4th, b to the 4th, c to the 4th, and then,
Yeah. So
and add up all.
yeah. So basically, let's try to do it individually. So A, B, C. This should be studying, a to the 4th, a to the 4th, b to the 4th, c to the 4th. And by the arithmetic mean, geometric mean, what would we get? We would get a to the 4th plus a to the 4th plus b to the 4th plus c to the 4th over 4 is greater than or equal to the 4th root of this product, which would just be a, b, c. And then we do it for the other ones and the other ones and the other ones and the other ones. We're going to do this 4 times. We have a 4 down here. Maybe that 4 is going to cancel out. So the idea is find a part of the problem that you can focus on. And once you work with that, then try to go backwards. So we would have something like this for all 4 of them. So we would know that the A, B, C, A plus B plus C, this is our, oh, we only have 3 terms.
Yeah, if it was for all 4 of them, we could have.
Okay.
I mean, I think it'll work.
Okay, so if we do this, this would be less than or equal to, we'll have a to the 4th twice from this, and then once more from the other 2. We'll have b once from this, twice from this, and once from that. And we'll have c once from this, and twice from that. And so we will end up with 4a to the 4th, and 4b to the 4th, and 4c to the 4th, and so the 4's will cancel. So we will then have a to the 4th plus b to the 4th plus c to the 4th. And this is because things will cancel nicely. And that's what we wanted to show. And so this is from getting each 4 times. And so, in the end, everything works out, not surprisingly. Otherwise, they would not have posted this problem where they posted it. But the trick was noticing that we could expand this and work term by term by term and then combine them. OK, I think there was only one more problem I wanted to do. I wanted to actually show why you might care about the arithmetic mean, geometric mean. These are cookbook problems right now. Now, often you have quantities like this that you need to bound in a problem you're studying. But let's actually try to use this to solve a problem that we might care about. Okay? So there's lots of different problems we could look at. So if I can get this to turn. Nope, I can't. I have gone too far to the dark side. Okay. So one of the big problems that you often study in mathematics is you want to find a surface or a region that has a minimal or maximal property. So if I give you a certain amount of material, can you make something with the smallest perimeter for a given area, or the largest area for a given perimeter, or maybe you do things in terms of surface areas. And then maybe you have other constraints. So I'll review the Farmer-Brown calc problem. So you might remember this from calculus. Farmer-Brown has a bunch of cows, or maybe it's a herd of cows, and he will only consider a rectangular fence. Any other type of fence is completely unacceptable. So Farmer-Brown has a certain amount of perimeter. P is the perimeter, and that's fixed. What rectangle maximizes enclosed area? And so you might have set up the problem in a calculus class as, here's x, here's y. X plus y equals p over 2. And you want to maximize a of xy equals x times y. One way to do this is you could then say, let's just consider this new function f of x, which is going to be a of x, and we know y is just p over 2 minus x. So we would get p over 2x minus x squared. The reason I've multiplied things out is I've done this problem numerous times over the years. I would much rather multiply it out and differentiate the polynomial than to have to use the product rule to differentiate x times p halves minus x. So now you apply calculus, you get f prime of x is just p over 2 minus 2x. Therefore, the critical point is x equals p over 4, and then you get y equals p over 4. You check the endpoints. F of 0 equals f of p over 2 equals 0. So the maximum area is when you have a square. How many of you have seen this problem before? Okay, this is pretty standard. Have you seen the variant where you now have Farmer-Brown is by a river and you lose one side? Have you seen how to do that immediately by using Aquaman?
By using what?
Aquaman.
No.
All right, let me just show you how Aquaman would help you do the variant where you are missing one side, because it illustrates a really nice property. All right. So in case you don't know, Aquaman is one of the superheroes. He can throw balls of water underneath the ocean. He can also talk to fish. So over here you have Brown. Down here you have Aquaman. Okay? Farmer Brown wants to make a rectangle. Yeah, you see what's going to happen.
So Aquaman is going to do this.
Good. Whatever Farmer Brown does and is optimal on land is optimal down below for Aquaman. So if Farmer Brown is trying to make his optimal rectangle, where he only needs 3 out of 4 sides, Aquaman does the same thing. And so if Aquaman has perimeter P to play with, if Farmer Brown has perimeter P, Aquaman has perimeter P as well. So it's now, we're making a rectangle with perimeter 2P. So I'll do perimeter P, perimeter P. So this is now equivalent to the Farmer-Brown problem, but with twice the perimeter. So it's the old problem with doubled perimeter. And so since we saw that each one was the perimeter over 4, now we get square, and the sides will be 2p over 4 is p over 2. So the long side will be p over 2, and these will be p over 4. And so by using symmetry, we're able to quickly resolve this problem. It's a really nice observation to have Aquaman doing his stuff the same time Farmer Brown is doing his. And you don't have to do the calculation. You could, of course, attack it using the same techniques we did over here, but there's no need. You get the solution immediately. Okay. There is a rumor that there are other shapes in the universe other than rectangles. Anybody know another shape? What shape should we have done first? A triangle. Why didn't we do a triangle?
Why would we do a triangle?
Well, I mean, sometimes people are looking for an instrument to play in band. I know this is being recorded, so I could get into trouble if I say something about the difficulty of playing the triangle. But
I think because Farmer Brown picked the square not because it was geometrically at first, but because it's easy to calculate variance of squares.
could be.
It's probably a matter of practicality.
It's also a square.
All right. All right. So we'll do the Farmer-Thiel problem. So she loves triangles, and that's why I chose Thiel, because I believe if I spell Thiel correctly, it starts with a T. So she will only consider triangles, and she wants to maximize the area for a given perimeter. So maximize area for a given perimeter. And now you can quickly see why Farmer-Thiel has a much harder problem. Well, her problem is significantly harder than Farmer Brown. Why is her problem harder? 3 variables, A, B, and C. Now before, when we used Farmer Brown, we could reduce it to 1 variable. You could do the multivariable calculus Farmer Brown. So as an aside, and I'll erase this, well, I'll come over here. How many of you ever revisited Farmer Brown in multivariable calculus? What could we use to solve Farmer Brown using multivariable calculus? What method? Lagrange. So we could actually do Lagrange multipliers. So what we could do is multivariable Brown. So we could have f of x, y, which will be the area, is x times y. And the constraint, g of x, y, is equal to x plus y minus p over 2 equals 0. Then grad f equals lambda grad g. So when you take it, you get y x equals lambda 1, 1. So this implies x equals y. And then now that you know x equals y, you can substitute. So you can do Farmer Brown using calculus, using multivariable calculus. You could also do it by just plotting the thing directly. We know that this is the same as x times p halves minus x. If you want to forget calculus, it's a parabola. Here's 0, here's p halves, and the maximum is p over 4. So if you just know what a parabola is, you can do that. There's a lot of ways to do Farmer Brown. Okay? We can get, what's nice is when you have 2 variables, if you get rid of 1 variable, you reduce it to Calc 1. Calc 1 we consider known. All right, let's go back to Farmer-Thiel. She has a much harder problem. We have 1 constraint, the perimeter, but 3 variables. We cannot reduce her. What could we do to try to solve this? Yes?
Maybe we could use Heron's formula.
How many people remember Heron's formula?
Because it looks basically like an AMGM problem.
Yes. And again, why is it not surprising that it looks like an AMGM problem? Because we're doing AMGM, right? I feel like one of the vice presidents many, many years ago said, I'm my own man, but on this issue I support the president. That, as much as I might try, the answer is always going to be, it's the AMGM inequality today. So Heron's formula, and I think there's debate as to whether or not to include the n, gives us the area. It is equal to s times s minus a, s minus b, s minus c, and then take the square root of the whole thing. where S is the semi-perimeter. So it's A plus B plus C over 2. I'll post a link to a proof of Heron's formula. It's not too bad if you know the Pythagorean formula. Essentially, the way you would prove it is, as always, you drop down an altitude so you get right triangles, and then you just crank through the algebra. How many people could prove the Pythagorean theorem right now if you had to? How many people can do it multiple ways? Okay, good, excellent. So one possibility is, if there's interest, I will. How many of you know the dimensional analysis proof of Pythagoras? Okay, maybe I'll do the dimensional analysis proof just because it's a really good perspective of looking at problems. And we've been talking a lot about these dimensional arguments and how to get a sense of how things are.
Is that the one where it's like you consider an area out of each of the sides?
No. Basically, it shows you that if there is going to be a relationship, it's got to be an area relationship. So there's a lot of nice ideas and a lot of good questions. So maybe we'll do that one on Monday. So we have Heron's formula. This is the formula for area. We're trying to maximize area. Do we want to maximize area? Well, given that I'm saying I want to maximize area, to some extent, yes, we want to maximize area, but do we really want to maximize this function? Something about that function scares me, or makes me a little bit unhappy. Yes? Yeah, the square root. I really don't like the square root. What should we study instead? Almost. So the area squared would get rid of the square root. We can do a little bit better than area squared. I'm sorry?
Squared divided by semi-perimeter.
Yeah, the area squared divided by the semi-perimeter. Since S is fixed, S is just along for the ride. So let's study f of A, B, C equals S minus A, S minus B, S minus C. So I just talked with Farmer Teal. She will accept this as a friendly amendment. So if we study this, we could try to do it with Lagrange multipliers. We've got our constraint, A plus B plus C equals 2S. Okay. So we're now clear. We've got the problem. There's almost surely a way to do this using arithmetic mean, geometric mean, or we would not be discussing it today. So let's see how we would go about this. We want to study S minus A, S minus B, S minus C, given A plus B plus C equals twice S. What do you think the candidate triangle or triangles are for the optimal, for the maximum? Yes? Equilateral triangle. Are there any other possible candidates?
I think you'd have to make A equal B equal C.
So one thing is, it's kind of screaming at you, I want A to equal B to equal C. I can think of one other possible candidate, but it's probably going to lose. If you had to come up with another candidate. Yeah, what kind of isosceles triangle? There's infinitely many isosceles triangles. Any nice isosceles triangles to work with? Okay, so a lot of times you are not allowed to bring back just one candidate for the job. You have to have at least two candidates. One is the sacrificial lamb that has absolutely no chance, but you have to bring them back just so that you can say, we considered multiple people, and in the end, the non-axe murderer who was not shooting people in the courtroom was the better candidate. So I need another candidate. What kind of isosceles triangle? An isosceles right triangle. So maybe that's kind of nice because I've got a right angle. And if I'm going to have a right angle, maybe an isosceles right triangle is the best way to go. It's not. But at least we have something else to consider now. Okay, so we want to try to study how big that could be. Right? So now, what would we have here? We've got our area. So we want to use the arithmetic mean, geometric mean. We've got an S minus A, an S minus B, and S minus C. When you see that, we're thinking arithmetic mean, geometric mean.
Could you make the terms S minus A, S minus B, S minus
Why not, right? We're trying to use the arithmetic mean, geometric mean. Do you think this is the arithmetic side, or do you think this is the geometric side? This is the geometric side. So let x equal S minus A, y equal S minus B, z equal S minus C, and then by AMGM, we would get x, y, z will be less than or equal to x plus y plus z over 3. Now, I should have the third root of this. So if I just cube this side, that's an okay way to write the AMGM. Because I've just taken the cube of both sides, so I've moved the 1/3 over. All right, so now we get our function, f of a, b, c is thus equal to, now we have to figure out what is x plus y plus z. So we'll get s plus s plus s, so we'll get 3 s's minus a minus b minus c. Well, a plus b plus c is twice s, right? So we get 3s minus 2s. Last time I checked, that's just s. So we get, after we do some algebra, that's just s over 3 cubed. Oh, this is nice. Why is this nice? It's constant. This is independent of A, B, and C, save for their sum, which is fixed. So what we've shown is no matter what triangle you take, the area cannot be larger than s over 3 cubed. So if we happen to find a triangle whose area is s over 3 cubed, or, well, not area, I guess. This is the friendly amendment to the area. If we find something like that, we win. Right? You can't do better than this. Now, the nice thing is, when is the arithmetic mean, geometric mean an equality? When they're equal. So you have an equality when they're equal. So equality when equal. And therefore, we get A equals B equals C. So A plus B plus C is twice S, so that should be, I think, 2S over 3. And so we end up getting the equilateral triangle. All right, so I guess the guess of using the isosceles right triangle is just a terrible thing to look at. So this is the arithmetic mean, geometric mean. What could we ask next? Yeah, generalization. If you have n sides and you're forming an n-gon, what is the optimal? Then the question becomes, how do you calculate the area? Is there a nice way to get the area?
Count the triangles.
So you count the triangles. I think there's a way to get it with Green's formula from calculus. Yeah, there's a nice sum in terms of various coefficients and whatnot. And then, rather than doing an n-gon, what might you want to consider in the limit? Well, you're jumping to the answer. Right? You can't just say I'm hiring the circle. You have to have a candidate space. Then you determine that the circle is the one who gets the job. So rather than using an n-gon, what might you consider? You're really rigging the hiring process today. I will not say the particular school, but I know a school that wanted to hire a very specific mathematician. They cannot say, open position for so-and-so's name. So what they said is, we're looking for a number theorist who works on the fault, and you put in enough things in your job description so that only one person can make it. Now, they can't do it completely rigorously like that. You can't put in all the things that uniquely specify the person, but you can put in enough. And in fact, I had heard through the grapevine, it's not even worth applying for this. They want to hire somebody who does X so that they can fit into the research group. So let's not just say circle, let's not say oval. Let's be a little bit more expansive in terms of what we're considering. So we were doing regular n-gons. Instead of doing an n-gon, what might we want to consider? Yes, smooth curves. So if I look at all smooth curves with a given length, what has the maximal area enclosed? Now, whenever you have things that are dipping inside, this seems like this is a poor choice because if I flip it out, I can push things back. Maybe you very quickly realize that your region should be convex. And so what it means to be convex is if I take any 2 points and I draw the line segment connecting them, that should be entirely contained in the region. And so if I have something like this, this is not going to be convex. I can do better by just pushing this out. So very quickly you might realize I want to consider just convex curves. But the oval is a convex curve. So is the circle. And which one of these is going to be best? And you end up getting a beautiful result called the isoperimetric inequality, which relates, given a perimeter, what can you say about the area enclosed? And not surprisingly, the circle has the greatest enclosed area. Professor Morgan studies a lot of problems like this, but now with generalized spaces. So here, we count all area equally. Well, maybe not all area is equal. And so maybe you can put some kind of density function on the plane. And maybe the points near the origin count more than the points going further out. Maybe you want things to be, symmetric, with respect to angle, but just decreasing with radius. And so you can talk about these weighted inequalities. And these end up occurring in a lot of important problems. So there's a lot of stuff going on here. And as always in mathematics, you want to see how far you can generalize things. How far can you push things? And it leads to some really good, interesting questions. But then the difficulty becomes, how do you prove something like this? The best proof I know of the isoperimetric inequality is basically using Fourier series. We have some nice results about expressing continuous functions as sums of sines and cosines. And using that, you get some really nice inequalities. Okay, so this is, I think, a pretty good place to stop. It's not worth going into the Fibonacci numbers just for 1 minute. Unless, have I mentioned Zeckendorf's theorem? Okay. We've got, I think, about 2 or 3 minutes, so let me just quickly do Zeckendorf's theorem. Yeah. And so the application, I heard about this application from Karl Pomerantz. He heard about, I'm trying to remember who he heard it from. I don't think it was Granville. But so the Fibonacci numbers I'm going to write as 1, 2, 3, 5, 8, ... And each one is the sum of the previous 2. And what's nice is if you write it like this, you have Zeckendorf's theorem. Every number has a unique decomposition as the sum of non-adjacent Fibonacci's. And the proof is essentially the greedy algorithm. So let's take 47. The largest Fibonacci number less than 47 is 34. Now I look at the difference. 47 minus 34 is 13. Largest Fibonacci number less than 13 is? I'm sorry, less than or equal to 13, sorry. It's 13. So I would just stop there. If I gave you 48, it would be 34 plus 13 plus 1. And when I'm doing my decomposition, I can never have 2 adjacent Fibonacci numbers, because if I did, I'm a moron. Right? Because I could have added them, and then I would have subtracted that sum. So you basically get every number has a decomposition. You then just have to show the decomposition is unique. Okay? I can now show you, is everybody roughly okay with this? I'm going to show you the stupidest application of Fibonacci numbers now. So let's say I write my number n as, fk1 plus fk2 plus dot 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 plus FKL. I write it in its Zeckendorf decomposition. Okay. I now shift all the indices by 1. So I just shift every index down by 1. And this will give me a new number. Let's call this n tilde. Okay? Anybody know approximately how big the golden mean is?
1.6.
About 1.6. So once k is large, this is basically multiplying these numbers by about 1.6. So n tilde is about 1.6 times n. I had shown a Canadian bill last week, or I guess yesterday. The Canadians still use the metric system. Anybody know how many kilometers 1 mile is? About?
1.6.
If you want to convert from miles to kilometers when you're driving in Canada, take your number, write it in its Zeckendorf expansion. Or if you want to go the other way around, shift the other direction. This is the worst application of the Fibonacci numbers I know, but I thought it would be a fun way to end today's class.